Welcome. This is another chapter to our primer. Now it's an exercise. I want to develop and show how the principal setup of an application with AI works and how you can deliver it to the web as an application there. So this is chapter number 14. You can access it from this web page, activate the library, and go here for the chapter. So this needs extensive calculation, so you should download it to your desktop and it's working properly. It's very unstable on the cloud because of timeouts if you don't have an upgrade. So go with this button to open this file on your desktop. Go here. So with all these differences in the from the cloud towards your desktop, it's always changing. I have to repair that. So these buttons don't work and now they are masked out. Don't get confused with it. For background information of how we argue, you should go for this tutorial from Zero to AI in 60 minutes from the Wolfram University. Go there. I prepared that with code. You can look it up and work it through. I highly recommend that. And to follow my line of argumentation on how machine intelligence works, go for this chapter 21 and the recently published Atlas of Digital Architecture about big data and machine intelligence. There you find my line of argumentation, how I am discussing this. So you also should go for the very important to the previous chapter for the self-organizing maps, which is a very simple walkthrough about AI techniques, a little in difference to McLuhan's setup. So this is more a traditional way of how this is discussed. This the way I prefer is with these self-organizing maps. It's not integrated into Mathematica, so it is 100% pure code written by me. But here we want to follow the traditional way, and we want to parse a real estate website of Switzerland, and we want to use these data to predict prices for an apartment here in a certain city of a certain size in a certain city via web in Switzerland. Good. So this will take a little time because I want to. It's an exercise on how to do these things. So I will explain all the steps, the strategies, and so on. My recommendation is that you look at like a TV series, then you get a principal understanding of how it works, and if you get interested, make it step by step, and then it will take a serious amount of time. But not to get the idea of how this works and where the problems are. So, unsurprisingly, the problems are not in the algorithms and the AI themselves, but in the big data. So these are all the memories, curating these memories, and so on. Whereas the AI itself, it's very generic and it's all the same, and it's a very few lines of code, and it's a lot of work to create all these things, to get all these things available in your environment. So let's start. Now we want to go for the Homegate web site, and let's have a look how it how it works. There's a URL base, page number, URL page, and so on. This is getting a parameterized website, and we can. This is assigned to URL, to the symbol URL page. We do that with the infix of string join and this variable page number. So if we change that for 12, then it would be a 12 here. So now we can make a button for that URL of URL page, and then we can go there to have a look. And you see projects for rent, apartments for rent. So they can have the second page. This corresponds to the page here. Go here. This page number 2. You have more apartments, and this is the URL, and you see the 2 is here. If we want to go to page 12, simply do this and open page number 12 with more projects. Good. Now, that's the first thing. Interesting here. You can have an embedded HTML to look at within your web page, but this is only working in the cloud. So let's have a look here. That's interesting. We can go here for the same thing in the cloud. So URL page, and here we can get an embedded URL page, and here you see web page within a cell of Mathematica in the cloud. So good to know that this is possible. Next step, import the URL as HTML text. This is very simple. We take this symbol, and this was page 1. We just check it. This is 1. Go here and open it so that there's no misunderstanding. We are here. Good. So to import it, we can get the HTML. You remember, or you should know, here in all web browsers, in this case it's Safari, we can show the web inspector, and this is the code, the HTML code, doctype HTML code. Here, and this is the rendering of it. So this is the underlying code, the rendering. So now I can take this mark here just to show you how this works. And if we want to go for example, this position here, this is, and if you want to look it up, that paragraph starts. This is span, and this paragraph ends, and this is rendered at this point. Go somewhere else. Here we are with the 760 Swiss francs rental price. So what we want to have is get these, we want to load this and go for these numbers. So this is called parsing. So we import the code, and now not to disturb it here, HTML is exactly what we'd seen in the inspector of the web browser. Good. This is the import. Now we can ask for example, this what we'd seen here. Go here, and we had this span. So we copy this HTML and let's go for the experiment here. So this is a certain position. Now we can ask our HTML page. And we can ask for string position of this. And of course, like in anything, you see this is 3 times there. So we also can ask and say string cases. In this case, it's not the position, so we take the content. So we have string cases, and then it's 3 times there. So if we want to get this text here, so we take the span as a key, and then we want to take that here variable. So the key now is the address with span, with the name span. So, and then we have the variable, and with strings it's working like this. We can say x, and then we want to have multiple of them. This means a single character, multiple, 1 or more, and this means 0 or more. So at the end of the variable, and this is giving you a lot of stuff. So which means we are not specific enough. So we want to go here and see for just the x. So now we are here. So the first problem is that there are multiple spans in the HTML page. So therefore we say there should be no span within here, or this should be, and that's how it works, shortest of this. And then we get here this span. Good. Still not specific enough. And if we look it up here, now the next one is P, that's the paragraph, end paragraph. So if we expand that and say this should be P, and here should be end of P, of paragraph. That should be a paragraph. This gives you a proper key and shows you, we can make a column of it. Column. This shows you how these things are. So they are, some of them are double, which means we simply can say delete duplicates of this. And then we have all the projects on this certain page. So all the addresses. So this is how the mechanics work, how to get certain certain content of a website, which is called parsing. Okay, that's the principle. All this works on strings, and sometimes it is necessary on some pages because they have a structure which is not really covered with Mathematica. In this case, we can use XML objects, which means we keep a structured import of the URL page. So then we put that to XML, and then we keep that in the list structures of Mathematica, so that these keys and matching gets simpler. And this works on this website. So therefore, I'm importing it now as an XML page. If we look it up, XML page. So now it's show more. So now it's not a string, but these are, it's organized as an XML object, and the XML object has XML elements, and the XML elements contain other XML elements and so on, and these are lists, and by that the parsing gets simpler, and the keys, for example, this shortest and so on, is not necessary. So, and we have this XML. Get the apartment IDs. So, with the XML page, we need this number. So this, if we inspect the website and we go to a certain apartment here, what we have here is this number. So each has a unique number. This is how they organize their website with their database. So therefore, let's look it up in the XML page. So show all, and look for this number where it is located. What is its context? So then you can click and go more and more, and you see this XML element. This is of type A, shape rec, class, list, top premium, and so on. Let's show how this is done. Here, what is the corresponding? Corresponding here. Let's look for it. Here, little description, long version, and we clicked on this. Let's try the file. You see, these are scripts. These are with JavaScript, so it's a little disturbing, but here we are. href A. This is one. And it stops here. So you see, it's a little, there are the images. It's a little tricky. Here, href, this for example, here we are. That's good, yeah? You see, start, href, class, list item, top premium link, and so on. And if we look it up here, list item, top premium link, so this is the corresponding thing, class, href, and so on. So you see, it's a one-to-one translation, but it keeps the structure of HTML. So now we take this and do the same process. So we can say cases of XML page, and then take that as a key. And then we say this should be on all the levels, and then we get exactly this position. We also can ask for position as we had it. And then you see it's a very deep listed, deep structured tree in this website, and there's no way to do it by manually or by hand. So, but we want to go for cases because we are interested in the content. So what we want to do is put this here to variable. So make this an A. Now it's simpler to do. We just want to have one thing. It should be a string of type string, and we don't want to see the whole story. You see now they are all coming, but we want to see just the A, not its context. So now we have the A, all the rental apartments and their identities or their index. Now skip the rent, so therefore we just want to have these digit characters, so we can make here, instead of A, we can say string cases from A, digit character. So now it's string cases, digit, and we want to have multiple of them, all of them, and then we get so we parse again, that's a key, just get the digit characters, and here we are, and now flatten it to make it simple. So that's it. Now you see that the number is different in my sample example a few days ago. Of course, all this is dynamic, and we will see that we will run in a few problems and how to deal with them, because our compilation is a few weeks old. Good. This is how to get the apartment IDs. So now this is how to go to get all the projects from the 50 pages. So if we have here 50 pages, now we can forget this. Now we have 50 pages here, which means we can get 1,000 apartments. Now that's a fast way. Just to give you an idea how this works, I always use, this is not mathematical, I always use the global variable dollar status. I'd always do dollar if this is some inspection things or some background information. This is for my last task. And this is how this works. We have the cases here. We go for URL page as we had, construct a page with the page number. This here brings the page number to status, and dynamic takes it. If this is changed, it's changed it. So I can say status is 1, then it's going to 1. So 12 or style 12 red, then it's getting red. So oops. Now this is not doing different, so there's a function taking pn. The function goes from here to here. Pn is mapped from 1 to 50. There's a list from 1 to 50, each one mapped to here. So this is page 1 until 50. This shows the progress. Now a URL page is constructed as we discussed. We import the corresponding XML page, and then we get the numbers as we'd seen before. We get the IDs of the apartments of this list. So let's start and how it works. Now you see it's running, parsing 50 pages. So this is how it works. So you have to be very, if you work on that, you have to be very clear and sure with small examples that the mechanics works. and then you have to run it. So there are more than 30,000 apartments, and then we have to parse all the 30,000 later, and you see this takes time. So it always takes hours or days, even days, and you have to make it continuous update and so on. So here are now the numbers. Yeah, good. Length of the projects, 1,000. Good. Yeah. If you're doing it and you have to redo it because the website's always changing, so you need another computer. If you make it serious, you need another computer permanently working on this list and doing updates. This exports it to your cloud. It's Homegate 1000. Can say permission, private or public. And then you always have to compress the data and save it as text. So permission is with the object, export. This is the destination, this is the content, and this is the format. So whenever you have any expression, in our case, these list of numbers, of IDs, compress them, save them as text. Here you have cloud object. This is public now. Now we can go here and see, create the chunk of data, and you can publish that later if you like. So now this is included here. This is how to publish it later. So so this is for 1,000. The key problem now is, because with this website, the problem is that there are 30,000 of them. And you have 1,000 plus results, and they don't give you direct access to 30,000. Therefore, you have to go to the city, for example, Lugano. It's a city, or so, and then you have 700. And then you see 700 search. You have to put it search. And then with 700, this should be, this is by 36. So this works, so we can access all the apartments in Lugano. So therefore, we split all the cantons. These are all the cantons. The way how they are used here, for example, now the query is list apartments, city of Lugano, matching list. So now we go for canton. Lugano is Ticino, it's part of this. So these are the names they are using to address it. I have to be very careful. So this is not enough, because in Zurich, and if you go for canton, then you still have 1,000 more. So now we go for apartments. This is what we want to do. Filters. Now we're going to go for rooms from 3 to 3. Now let's go for 2 and 2 rooms. And then you have 200. So therefore, my strategy I'm working on is iterate over all cantons, iterate over all rooms. So these are the rooms: 1, 1.5, 2, 2.5, 3, 3.5, and then the very large ones. So these are the rooms. So now we get the tuples of the rooms, and the let's go here, the tuples. So now we are making tuples That's very important. Always of these cantons and rooms. This means the canton gets a product with the rooms. So all combinations are there. So, and these are the parameters for our URLs, which means we can now create, these are the URLs, flatten them, that's okay, make them, so flatten each of them, so which means I don't want, yeah, go here and address that to the URLs. This is the URL, this, then we construct, let's evaluate that and ask for URLs. Now here we have all the URLs, and there's a construction here. So we say Canton Obwalden, matching list, room from 4.5 to 4.5. So this is how this server is doing it, and hopefully it's still available. Yes. So these are the 4.5 room apartment in Canton Obwalden, and there are 17 results. So now it's the same like we had before, but now we are with say my URLs of one, and okay, this was this one, and then we say length of it, and now we have 286 instead of 50. Instead of 50 pages, now we have 286. Then the same procedure, dynamic status, running this, export it to Homegate 30K. So I don't want to do it now, therefore I had this ASC. This is the list. Now we can import these projects, which means I published it as I described. Import this cloud object, having this, the 1000, this is 30K, uncompress them, and here we are. These are all the projects, 30,000, 31,000 project numbers. So take this, should work, because I published it in the cloud. Good. Next step, if we have all these numbers, now we need the attributes of a page. So it's the same procedure. Now we have to go to any of these things, of these apartments here, and now we want to get here these numbers. We want to get the geo position, square meters, years of build, and so on. So it's the same procedure. Let's go here. We import the first project. Hopefully it's still there. Go and ask for it. Yeah, it's still there. Translate it to HTML. Not to have double import. And with this case, that's important. Now we have here a complex embedded system, and I can't reach these data here via XML object. So if I need the HTML object to go here, and for the rest I take XML. And I don't want to import it twice. Therefore I can say, instead of import, I can import string, and I take the imported string here as the source. So there's not a URL as a source, but as a string, and I want to translate it to XML object. This is done here. Good. Good. So now we want to get the expenses. For example, now let's go, we have to look this object. Good. HTML object, this is this one here. We want to have this one. This is the first object now we want to work on. This is our HTML imported. Now I want to see it on my browser. So this is how we did it. URL off. We need, because there's infix here, we need the force into the bracket, and this is a kind of stupid thing. So now let's go somewhere else. 3. This is better. So go for 3. Import it. Let's set the string. Structure it as XML. So now we want to go for the rental. It's here, just as an example. So how does it work? Like always, we go here for the inspector, check where it is. See, here it is it. Here are all the costs. So it is this tag with this structure. So to get it, the simplest way is just to say we have the XML object. This is what we imported. Then we go, and I think it's specific with the rent. It's 1, copy, find, and look for it. Come on. Let's go for the expenses. Huh. Why is it not working? Also again, number 3. XML object. XML object. Show all. Find. Here we are. So there's one fix. Now look with multiple clicks, look where the structure is. And now with this element, we got all the content we are interested in. Copy this as a key. So then we say cases, like always, XML object, get the key, say it should be on all levels in the structure, and we want to see that. And what is this? Why is it not working? That's the XML object. Ah, look at this. It's not cool. I copied just a chunk of things and they are not complete. So show all, find. So now is, yeah, that's a key problem. So I need the list. Okay, copy this. So I just had the element here, and then I had a lot of elements, and they are not complete as a list. So I have to pack it as a list, copy this as a key. So now I give this all out, copy this. Now this is one element because cases needs the source, the key, and then the level. I have this. Now it's matching, and now we have to get the things we are interested in. This is A. This is B. And we don't want this. Now we can go here. Okay, it's still matching. And instead of all the stuff, we simply say this is, we want to have A and B as a result. And then we get these two numbers. Good. This is specific to this web page, so we can make that a variable so it would work on the other pages, on the other apartments, like this. So now we don't want to have it as a string, so this is a string now with this crazy comma here and so on. We just want to have the digit characters, so we say string cases of this. It's the simplest way, digit character point. So then you see it just gets the digits, and we have to make that string join. So then it's here, and we have to make that evaluate that. So we will have to read that string as code to make it an integer, to expression, and then it's an integer. Do the same with B, and then we have the two numbers. Flatten it, and now this is what we wanted to have. In this case, we added make it a rule with key value pairs. So then we can say net rent, if you want to do that. Copy here, net rent, this, and additional expenses, this, and a rule. And then we get this as a result. So this is how it works. And of course, to get all the parameters, it's a lot of works and detail, but you can you can buy that for very few money in India. Very simple. You simply say, I want to have a parser for this web page, and they make it pretty fast without any problem. And costs. So here I made a function for the data we are interested in. It's just the same. I've wrapped it then with a function and just for all these parameters I'm interested in. So, and this is a function, this is how to use it. So it's always with the function you symbolize these mechanics here. You symbolize it. So you wrap everything, make these variables we are using here, not to get confused with other functions. We make them local with the module, and then it's exactly what we did. So just a little more of it. Here is, for example, main information. This is something like this. So you can try to read that if you like, or make it by yourself. It's Sketch and we want to be fast. To use this function, it's like this. We apply it to this symbol. Functions are always capital letter at the beginning. And then we have a variable. Again, this is a key. You see it like here. It's the same principle to get these keys. And this is used within the function. And we have to call this symbol with this key, and this is what we have. Here, you already know this. So this is a certain project number 100. So, and then if we apply this function to project 100, we say this is the image data set, then it's parsing page number 100 and gets a lot of attributes. So good. Now this is of course very poor. So if you really want to make good prediction, then you need additional attributes, and you have to take a little more care. And this is what you can do. For example, here, copy this. This is, for example, project 120. Here we get the data set. This is what we did. So this is a data set. So these are the basic attributes we parsed. So in principle now you can go, for example, geographics. So we have here the country, the street, and then we have postal code, locality, and we have latitude and longitude. And now with this simple geographic, you can look it up. That's very helpful with Mathematica. You can get all these maps, tools around, look it up. Very interesting. Not a lot to do. So we have a marker at the exact place. So we take so this is how to access these lists of rules. So we apply this set of rules to this string, which means this string here is replaced by this number. So and then we get the geoposition, latitude. So this is done here. We do it to expression to make this, I think, is still a string. We make that. So we had a geoposition. So we want to have a geo marker on this position. We get the geo center on this position as well. Then we have a geo range of 200 meters. That's a quantity that's very interesting as well. So you can do 5 centimeters or miles or whatever, and you can convert that with the quantity function. It's across everything with weights and with all physical parameters. Very helpful. And then we want to have that from OpenStreetMap. And to get that, here we are. So it's an apartment, obviously within a village, and there should be farmland and so on. So this is not part. You can analyze this as well. and with image recognition, and then you get additional parameters to get a better profile of what's going on. So in the same, just take a digital globe for satellite images. Everything is the same, but another server with the same setup. And then we get the satellite image for analysis, wherever you are. And you see, indeed, it's farmland somewhere. That's this building. So if you want to continue and get it better, it's good like that. For example, now with OpenStreetMap, you can find all the kindergartens, the bus stations, the shops, and so on nearby. All this is good for getting a better profile of the apartment automatically. Or you can get from Swiss Topo, you can get noise levels and so on. Good. Even 3D environment, and you know whether it's slopes, good view, and so on. Whether there's a lake nearby, all these things which affect your apartment. Or you can go with longitude, latitude. You can go to and ask for tweets, because the tweets are geo-referenced as well, and then you can look what it is, whether it's good or bad talking, or how the frequency of talks in this area is, whether it has a good sentiment, bad sentiment, and so on. Or you can go for here, for example, there's another one. This is in Locarno. There's a lake, and you see it's completely different here, this environment. Or you can go for Street View. It's not working properly. And then count the trees, count the stories or floors of the building, count the cars, the quality of the cars, the value of the cars, and so on. All this is for free, and it's available worldwide. And you can put that to the vector, so the attributes of your apartment, to get a better profile of it. So, but we want to continue with this simple setup, and the prediction will be okay, but not surprisingly good. Or here, this is interesting as well. So go for, this is the way how to, hopefully this works. We can start a web session. Mathematica can remote control a browser. So this web session, then we go for project number 32, and then we execute with this session, and we say open web page on Google Maps, on latitude, and so on. And then we just simulate the use of the browser to get high quality environment, and you can work on these things. Good. Just to give you an idea of how to make it more realistic. So delete the web session, and then you're done. Good. This is how to get the ImmoScout data of objects. All these additional features can be integrated here within this symbolic function. So you don't have to care with the following stuff if you make an update on this function and this data. Good. Next. Full satellite, here we are. Oh, that's for that. Now, parse all Homegate apartments. So now we had this, so import 30K, So this is what we already had. These are our projects from the 22nd of November. So now parse the attributes of all the projects. How many projects are there? Length of projects. So we have 31,000 projects. We again do it. We do it with map index. We present the status with the running variable, so with the index to this list of the projects. Then we put quiet here, so ImmoScout data on the indexed. So this is the index, and this is the indexed element of the project list within this mapping. We put in our function, and if there are errors, we don't want to see them. So this takes a few hours, 3-4 hours, and then you have 31,000 of these attributes of all the apartments. So, but we don't need to do it. We can export. We just no, we have to curate that a little. So the problem is that it's not super stable, so we have to find to go and ask what to do if there's no longitude, if there's no price, and so on, and just filter it out and calibrate it and so on, as we discussed it with the text. So we have to make some work to curate everything and bring everything in proper order. This is very pragmatic and needs some work, so that this is done. I exported the data as Homegate 30K DSC public and compressed my data set. And this is what you can do here. You can import this data set, and this is what we want to do now. So there's an import of this, and now the data set is not 31,000, it's about 400, which are bad, and they are filtered out here. And I didn't want to see them with the parsing, therefore I put the quiet here, otherwise a lot of errors, missing things. With quiet you can say, I don't want to see that. So this is a proper data set, and you can work with it. So this is what we want to do now, again with geo. That's interesting. Geographics. We have a styling. So this is the relief map. So this is what we want to put in the background. Then we want to frame that with the polygon of Switzerland. So you can look it up in geographics. This is very comfortable. So now red point size, and then we had the geopositions of all the data sets. So let's check it how it works. Immo data set. This is from 1 to the first to the last, so it's just say 3. And then here we get these coordinates. Let's have a look what happens if we take all of them. These are the data sets of the first 3 projects. So then the first is a URL, second is the latitude, longitude, price, then you have the missing, this is what curation did, it's not there, a studio, balcony, and so on. So therefore we said from all of these 30,000 we want to have the first 3, and we want to have, and on the second level we want to have the second and the third. This is what this command is doing. And if we go for 12, then you get 12 So this is how to get data, to get parts of a data set in a structured hierarchical list, as our data set is. So here, therefore, we get them all, 2 and 3. This is a data set. We put that to a geo position and make that points. So these are 30,000 points in red with a small point size. So that's the geographics here. So the geographics has two elements. The background. So this is the map of the geo-relief map of Switzerland. And then we had the 30,000 points. And this is the graphical information we have. And then there are some attributes. We don't want to have a background. We want to have a geo range. This is of Switzerland. Unfortunately, I didn't correct them, but in principle they should be done here, far outside of Switzerland, and therefore auto range doesn't work. So I had an explicit range to display Switzerland, and I want to have that in 512 pixels size. So now this takes time, mostly because we have to load the relief map of Switzerland. So, and here we are with all these points. So go here, a little smaller, bigger. Now it's downloading tiles of Switzerland. And here we are. Nice and simple to do. Good to know. Now we can make some statistical analysis. Look at this. Immo data set. And now we take the fourth parameter. This is a price of all of them. We are checking whether they are integer, because sometimes they are missing. So if we have, for example, this here, we can go for 12. Then you see they are missing. So we have to get rid of the missing. And this is we simply say we want to just filter out. So this is a key to this list. So let's check cases. Integer 1 on level 1, and then this is just the numbers, which means these are the prices. If we take all of them and make a histogram of them, then we get an idea of what the price range in Switzerland is, and you see it's mostly around 1,300 Swiss francs. So we can do it with the other parameters as well. These are, I think, the area, the size of the apartments, and these are the amount of rooms. Good. I don't know, this is 8 is the amount of room, okay. Aha, or real. So this amount of rule, so the integer or real. Or real. And then we get the 2.5, 3.5, 4.5, which actually is more than 4. So because they take the kitchen or something as half a room. So this is how it works. So it's all around 3.5 rooms, the apartments. So the year of the construction, you need a little more. So this is parameter number 9. This is only integer. So then you see this doesn't help. So therefore we have to parameterize the histogram, and this is done. We want to have a range from 1-800, so we don't need these super old things, to 2020, and we want to have that in years of steps of 3. Then we get a nice histogram of apartments available on Swiss market. So this is statistics, and this is very helpful. And you see, if you parse the Switzerland or any other, you can do it in any country, and you get an idea, like we did it with the books in the last exercise. Like you get an idea of how it works to get friend with it without being there. Or this one here is get the ratio. No, this is the ratio of price and the area and square meters. Now let's have a look how this works. So we have the IMO data set of 1 to, so just have a look at the 12, and 4 and 6. This is always the price and the area, square meters, price and in square meters. Then you have missing and so on. So again, now this is good pairs, so we like it, so we can make a coordinate system out of it, x and y points. So, and again we need the cases, and instead of checking one, now we check the list, and there should be, the first should be integer, and the second should be integer as well, which is this key. We have it on level 1, and then we get 21,000 good points. Good. These are points. Put them as points, and then we have a graphics, not a geographics, but a graphics, very similar. We say point size should be very small. Then we have all the points. Default is black. We want to have a frame with the coordinates and the ticks. Aspect ratio to be 1 if we don't have that. Then we have this, because the price is at another scale than the square meters, so it takes the aspect ratio to 1, and then you have a proper setup. So here you see the extreme points, but the majority is here. Again, statistical data visualization and whatever, however this is done. So let's go and put these points on the map just as an exercise for data visualization. So we want to get this map here, where the expensive apartments and where they are cheap. So let's check how this works. What do we know? We have, again, we know these are the cases. These are for this is a data set. This is a key, and then there's a reformatting of it. Let's look how what it is. Copy this, say we don't want to have just 12. And then what we have is the geolocation, latitude and longitude. We have the price, and we have the square meter. So, and then we know this is real. This should be real. This should be integer. So there's a missing, so we don't do that. And this should be integer as well. So if there's a missing square meter, then we skip the whole thing as well. So this were the cases. And we want to translate and transform them into C by D, so which is price per square meter, and keep longitude and latitude, and make that not a fraction, but a real number. So let's look how it works like this. And here we are. So now we have the costs per square meter and the longitude latitude. So if we put that 1.0, then it's getting a computational number. And here we are with the prices per square meters and the geolocation. Good. Now, for these graphics, the key problem is that we have to calibrate these the first parameter here, because with color we have to distribute it between 0 and 1. So and then the key problem is that so we easily can do that, but the interesting thing is here. So we have to forget about the extremes, because this would yeah, the picture would be of low contrast. If this, for example, is red and this is blue, this is nearly all of this is blue, and there's no red, only one single point. So therefore, this is we use a quantile. That's the interesting thing. Look at this. Now we have the vectors. So here we say vectors from 1, all vectors, and always the first element, so which means we have this ratio here of price and square meter. So quantile says what is a number, 10%, in this case 10% is smaller and 90% and 10% is bigger. So what is the center, what is the range of values which represents 80% of the data set? And he says it's between 13 and 27. So this is called quantile. So what we're doing is we put this lower limit and the upper limit. This should be blue and this should be red. This should be blue, this should be red. And if it's higher than 27, it should be red. If it's lower than 13, it should be blue, because we don't want to put that to graphics. This is here. We do this with this function here. We say replace from this if, so there's a key, A is a real, and A is smaller than Q1, it should be Q1. If it is bigger than Q2, it's Q2, else it keeps A. Let's replace. And then we put all of this between 0 and 1. This is done with rescale. So rescale is a nice function. It says 1, 2, 3. And we have to make that a list. So, and then it says it's a range between 0 and 2 and 3, which is 2. And the minimum gets, and the maximum gets 1, and the others get proportional inside. So if we put 2.5 in between, then I get this rescaling and calibrating to the range what we can, what we have with color, hue color of this is 0.3. Then we get a color, and we have to do that with all them. So that's hue is it's a circle, and now we had the color scheme. I can show you color data rainbow. So this takes rainbow. This says 0 and this is 1, and there's a lot of different color data functions. So take this rainbow instead of hue, and then we have this calibration of the numbers according to the rainbow. So if we have the vectors, now we quantile these vectors. Now we get here, we just translate this, replace the vectors, the key. So this is a typical number here. Then we put the A towards a function and the B and C towards a geoposition of this as a point. So we replace that. So now we can say vec2 of 1, vex2 of 1. So we had a red point at this geoposition, 1 or to 12. So all super red because at the same position, same size, and so on. Yeah. Good. This is vector 2. Now we are ready. So we curated the data. So just to get an idea of how this is working, where the work is. So we're still with just now with data visualization and with curation of data, acquiring data, and so on. We are not with AI at all. So it's pure statistics and that's it. So now we prepared the data and we have this function we had already with a relief map, but at the first element we have not a relief map, we simply have a white polygon of Switzerland. Then we go for red and the point size, and here we have all the points at geopositions with their color representing the price per square meter. The rest is the same as before, and here we are. Yeah. So that's it with these excursus. Now we look for, with the first AI tool, looking for, I call it looking for friends. Now you can start with this. You don't have to do all this curation. You can start here, load the data set. Check the length, whether it's working. It's this. So, as we'd seen in this tutorial, I recommend one from 0 to AI in 60 minutes. This is how it works. So super simple. So we take the data set, IMO data set, all of -1. So let's look what this is, just to be sure. Replace the all with 1 to 12 and ask for it. Aha, so this is, we need the feature extraction for the text because these are no numbers. So this is the attribution and the principal description of it. So this is a feature extraction of these descriptions. So, and this makes a function. Yeah, which is able to, and we always only can work with numbers, which is translating text towards a vector. So now we can go here for feature extraction of IMO data set. We just want to have the first one. You see, always like that. I put it here, FE1, and I you always should do copy and paste. So it's at this area. So and then we get a vector for this thing. So if we go here for another one, we get another point in this multidimensional space of other than 33-dimensional space of representing tempered by this data set, which is the memories of the last day, and just tempering it. So now we reduce the dimensionality to make it compatible, for example, with the price and so on. We don't want to have so many dimensions, and there's not a lot of diversity in here. So now we simply make a brute force, just to make it simple. We make a dimensional reduction and put it on a single line, so that if it's cable TV elevator, and here pets allowed, cable TV elevator, child friendly, they are near, but if it's balcony, terrace, then they are distance on the one-dimensional line. So go here and reduce this, project this 33-dimensional to a single line, and keep all the distance. And it's to, yeah, it's a manifold. No, it's projected to this line, and this gets a function able to do this projection. So that in principle keeps the distances in the 33-dimensional to the one-dimensional. You lose information, but I think it's not too much needed here. So, and then we can get here the vectors for all apartments. So which means now we had the data set of 1. This is what we did before. We have the this is the data set terrace cable. So when we make a projected, we look at the position in our tempered space, and you can do it with any kind of text. So for example, you can do it with hello there, and then you get a point in this tempered space of all these descriptions. It makes not too much sense, but if I put in balcony, then you are at a certain point. If you put in child's, then you get another point, and so on. So therefore we can do this point with the first here IMO data set. Then we do our dimensionality reduction of this. So this is the number here. Now we have a number specifying or characterizing the things here, and that's it. And we want to do it for all the data set, so we put here all and say flatten of this. And if we do this, we get for each apartment on market a certain position on this vector. So yeah, that's PV1. So the type of apartment, we do the same thing. So this is at position 7 on our data set, the feature extraction, FE2, then we do the dimensional reduction, and then we get a position on this, again, this one-dimensional vector for each apartment, which represents the apartment type. So it's another number. So now everything is numbers. So, and this one here gets the data set, all the numerical parts of the data set. We skip the URL at position 1, and then we get our our extracted numbers for the alphanumeric input, and we combine them. This is here with a vector. So therefore rex of 1 is longitude, latitude, price, additional expenses, square meters, rooms, when it was built or refurbished, and then the the description here, and then the apartment size. So that's our vector. So extract the features. Now we do with this, we temper a new space of all the apartments. So this is FE. So, and this is mainly done to get rid of the missing values and to get it rescaled. So now we have a proper function to project this distorted things to a proper cubicle of 9 dimensions. And we apply all these vectors to this cubicle. Which means if we now say PV of 1, this is properly done. Now you see the numbers are all between -2 and 2, something. Nice distribution. The missing value is out, and now we have proper places in a multidimensional space. So we can, let's have a look. So this is correlating. We can project these projects directly, again with dimensional reduction. You see it to a 3-dimensional graphics. So this is our space with all the, where is this here? This is our 9-dimensional space. We reduce this to 3 dimensions, make points of it, and do it by graphics as 3D, render it as 3D graphics. And this is our space of apartments. So this is not any longer with price and costs. This is with all parameters we have. And all the parameters, it would be the same process if we go and take things from street map and so on. Just this would add more of these parameters, and then we can project, and then we have more more differentiation there. So, but this is this is a tempered space which knows all the events of the last day. Good. Now it's super simple. So we used all this dimensionality reduction and feature extraction. These are AI, the principal AI methods. So now it's very simple. So I want to get, if for example I go for vector 112, it's this at 1012. The corresponding IMO data set. If you want to get the IMO, so make it an N. N is 1.12. IMO data set of N. So this is the apartment, and this is the corresponding vector. This would be the corresponding featured vector. So, and what we now do is we yeah, to make it simple, I just took this vector here and took this, but you can put anything in here. Then you go and take the feature extraction, dimensionality reduction, and so on. You simply have to use all these functions we had here and here to write anything of the new apartment, whatever you have. You can keep the missing, make the whole process here, what we did with the stock of things we experienced. For the new one, make the whole process to generate a PV, a project vector, and put it here. Yeah. And then you can ask, give me the nearest of these projects, the nearest indexes of these projects, and give me 12 of them. And these are my friends. So which means if I ask for this, these are the friends. If I ask here, these are the friends. So that's very, very interesting, because now these are my friends. And I ask IMO data set of these friends. Of course, he himself is the nearest, but this is the best friend. And 636, this is the best friend. So, and this is a kind of combination between the geolocation of how it is described, the size, the build, the price, apartment type, and so on. So I put that into a function here. These are the friends of this apartment. And now we get all the data here. So we get immodate grid of immodata of the friends. And we get these parameters of immodata. And here we are. These are the friends. This is a little too much. Therefore we have very, very few here. Now go here, and then we see how it works. So this is a link, the rental price, the size, apartment, and the link of this apartment. It's here, and they are at the same region in this temperated. It is already sold. As you see, they are all of the same kind, and they are and they are located in a similar region. That's it. Good. Now, what is this? This is a parser of the images of the friends. These are the missing projects. They're already sold, and here you see they are always all of the same kind. Of course, the images are, depends on how they did it. So this would need another. We will have that in another exercise, how to work on pictures that you can distinguish between the interior and the exterior, so you can mix it up. So all the others, and these errors are because they're already sold. Good. We have this, and these are the geopositions where they are. And you see, it's not all Switzerland, so because it's an important parameter where the longitude and the latitude is, so it's all around here at a certain area. So I think you got the idea. Okay, now next thing, how to do supervised learning to predict the price of an apartment. So again, you can start from scratch here, load the data set, get the feature extractions for the apartment descriptions, get the feature extractions for the apartment type. So now we reconfigure it as we did it before. Now we get rid of the alphanumerical data and replace them with their one-dimensional numerical position. This is here with ds. Now this is interesting as well. Now we need to fill the missings, and there's an AI method. If I have a data set like this, so it's an array of numbers and crisscross, it's checked, and then there is a synthesis of the most probable values. So in principle, you want to have a flat landscape of data, and so you interpolate simply the holes within this landscape. This is done with this function. Very simple and smooth. It's a learning curve. There are different algorithms in competition. Okay, this took quite a while. Some, I don't know, 10 minutes. Okay, don't be. Okay, this now we are finished. This took quite a while, some 8 to 10 minutes on my computer. Now we are here, and we have a data set called DS1, which has no missing values, and the missing values are, so we didn't get out, because it's too much. So if we, as we had with the prices, there are very few, so, but if we get rid of the apartments which had any missing value, then there's no apartment left. So, and therefore I smoothed interpolated it out. So this is a nice AI application, synthesize missing values. So now we want to ask for, we have this data set out of 9 different values, and we want to get value 3 as predicted, so which is a price. So therefore we get a key of this, and we translate it into a list without 3, and get 3 out as a rule, because this is the format we are using. Therefore, it's expected. So now this is DS1, and this is translated now in DS2, like this. So we took out 980 and put it here as a rule. So then it's important that you take the train with the data set of the last day, and then you have a test set, this of the actual day. So in this case, I take a random sample of DS1 of the 30,000, and that's a training set, and I make the complement of the which are the elements not part of training set but part of DS1, they should be the test set. So this is artificial people doing it like that. So in principle, this is the last day, the things you know. This is the current situation, and the actual day, things you don't know. So this is what you want to predict, and this is what you know. So now we go for the test set. Is it here? Something's wrong here. I think it's DS2 we have to put here. 2, okay. test set. Now this is 2. Now we check. Test set is this. Test set 2 is okay. That's the rule of it. Good. Okay. And having that, we can say what we want to have. We want to have a predictor of the training set. So which means he's calibrating things. So he's calibrating these values in a way that they, in these 28,000 examples, are pointing to these prices. Yeah. So it's very similar to dimensional reduction and so on. There's always AI techniques. So this is a predictor, and we get a function for that. So which is a price predict function. So now he's training again. Now he's using linear regression. There are alternative methods with different performance. Random forest. Now here's the best. The best one is random forest. So interesting is you simply don't have to care about it. You simply have to say what you want to have. It's predict. So it's very big, this function, therefore it's not part of the notebook. So the prediction is that now it's very simple. So I take the test set. So look at the test set. So this is something an apartment he doesn't know of 1 at this. So I know the value, but the predictor says is able to. So I take this off and let's ask, what is the most likely price number here? Do that, and it says it's 1,000. Do that with 100, 2,200, and what is it predicting? 1,700. So it's not out of range. That's it. So very simple to use in AI, a little tricky, and you need a lot of skills and craftsmanship to create the data, to make them visible and so on. But this thing itself, so the idea how it works, is not too complicated to know. I think it's very important. For you as architect, you have to get the idea that it's not about problem solving. So it's about trying to organize yourself in the plenty at the new day. So therefore I'm using these metaphors. So now prediction measurement. This is what is present. What is with? We want to know how good the whole setup is. The creation of this data, these kind of vectors, calibrations, what we perform, whether we need better data and so on, to make some arguments about that. So we have the prediction measurement. This is what Mathematica provides. It says a price predict, so this is a function here, and when we test the whole data set with this price predict, and then we get a measurement of that, and we symbolize that with PM. So here we have the predictor measurement object. So now we can ask for the properties. We have what can we do with it? So it's a lot of tools of analysis of this, of the quality around the quality of our predictor. And for example, there's this comparison plot. So we can go here and ask. And here you see the predicted value and the actual value, and a perfect line would be here, and you see it's working quite okay, and you're getting with very low values, it's getting bad, and there's very huge apartments. It's getting with very high, but here it's kind of okay. And you know, we can improve it with more and additional parameters which are more specific. So then you can ask for the worst examples. And here there is a price of, what is the price? Here, and the prediction is this, the price is this. Okay, now let's look for the worst. This is a price, and I don't know the prediction, look it up. So, and this is the worst example. Price is 8,000, and now we look it up. And that's something extraordinary. Nobody knows. It's a shop, nobody knows. I think it's simply not an apartment, and by that it's out. So what you normally do is, like we did it with this filtering of data, with the quantiles, you start to kick out the extreme values beforehand. It's a part of the curation that you take the quantile of the top and the low 2%, and if you take them off at the beginning out of your data set, then the whole thing gets more stable. So in principle, you don't want this, or you need more data or some other parameters to keep them. So, but this is how it works. And now the last step with a simple web application. So what we had the test set. Number one. So these had been our parameters. One, geolocation, 1, 2, 3, 4, 5, 6, 7, 8 parameters. And this is what we had. We did the prediction like that. So we simply said, we take this, the first of that. So this was here. This was our price here. And the prediction was this. Good. If we have that, then we want to make an application of that. You have to simplify that. People don't want to put these things in, so we want to get a city, for example, and the square meters, and then we want to get the price. So therefore, we need first a list of GPS coordinates of cities of Switzerland. Unfortunately, it's simply not there. This is a small parser. You can go and look. This is a parser. This delivers. So now it's parsing 5 URLs. No. Okay, now I have to fix that. Not done. So this is the list of rules. Wallisellen at this coordinate, Muri on this. I get it from a web page. This URL is not there. Forgot it to copy. So these associations work like that. You take this this symbol, and you say take Mendrisio, for example, as a key, and then you get the geo coordinate. Go for Lugano, and you have it like this. I think with the apparatus of our discussions up to now, you're able to read how this works. So now we have the city GPS, city to GPS, and now there's a prediction function. A simple prediction function. So what we want to have to put in is a city as a string. We want to have an area. We want to have the rooms. And these rooms are either real or the rooms are integer. So this is what we want to take, and then we want to predict. So therefore, let's translate it. We have the price prediction of this list, and this corresponds to this list. So we make this function here, yeah, price predict. So first we need the geo coordinates. So here, therefore, we have the Swiss city GPS. We remove the diacrit. So for example, Zurich goes to Zurich. We did it here in this function as well, lowercase. So then we go to lowercase. So we could take Lugano, or yeah, no, not here. But yeah, then we need these kind of things here. See this. So if we are here, then we can have Lugano, it's the same, or Lugano, which is nonsense, but it does the same. So therefore we need this step here. We sequence it, so this is a list, and we open this list and make it part of this list here. Then we say we don't know the price, the square meters. We don't know we know the area, we know the rooms, and we don't know any other thing. So we're not interested. Make it super simple. Make a prediction there. So this is our function, which means we can ask simple prediction, Locarno, 100 square meters, 3 rooms, and this is the price. If we go to 120, this is the price. If we go to 2 rooms, this is the price. If we go to 4 rooms, this is it. Yeah, in Locarno. If we go to Zurich, then it's more expensive. So as expected. Good. This is our function. Now we have a nice wrapping of our predictor in a symbolized function. So we can use it easily. So now this needs an interface. This is how it's done in Mathematica. This is called a form function. We can you can look it up in the documentation. It's here. So interesting to read if you are. So here now. Here this says form function. First should be a string. Second should be a number, and there's a function. So then we get a kind of interface, first, second, submit. If you want to run that function, then we go here for the first 3, and this should be a string. This will be hey, and second is 4, and then it, yeah, unfortunately it's here. It goes for a function with these with an association list, first and second. So the function is not defined, therefore I get just these parameters. So in principle, this, I think that's it. Now we adapt this and say, okay, we don't want to have first, second, we want to have a city as string, we want to have an area as an integer, and we want to have rooms as numbers. So, and then we look at this. We can look it up in the documentation, and we want to make a list of the city, of the area, of the rooms, and we want to, so instead of f here, which is not defined, we explicate that, and we want to access these 3 variables and get their values from the form as a list in form of a text. And instead of saying this is a form, and then evaluate this form. We put this evaluation here. And we can skip the form here. So now it's going for the city. We say Locarno. We want to have 100 square meters and we want to have 3 rooms, and submit. And unfortunately again here, this gives a list of Locarno 1003. Good, that's the next step. Now we can deploy this interface to the cloud. The first step is we take this thing here, we have it here, we simply wrap it with cloud deploy, and we say this should be public. So if we do this, we have a public cloud object. You can send it to your friends, and the internet is looking like this. Locarno. Then we have 100 and we have 3. Submit, and then we see Locarno 103. Good, first step. Now we want to go for the now these are our parameters to our prediction function. So which simply says we can keep everything as it is, but we say we want to have the prediction function of these 3 and want to have that as text. Check it. Go here. Carno 100, 1000, 3, 1. So it's 4,000 Swiss francs. So this is the result of our predictor available in the internet as a service in internet. Good. We have this. Now format the output via HTML. So if you want to, because all this is HTML in the cloud, then go to V3 school. This is how to learn HTML. So here, try it yourself. This is the code, and we simply say, oops. The estimated price of your and then here is 1000. So this is the HTML code. If you run that, we get this. Yeah, no. Or we have here try editor, so this is a title. Then we say my simple predictor. If we have this, it should be there, but this is how it works, and you can do any kind of things what is available in the internet with HTML. So I had here an HTML form. I just copied that and put it as a string. You see it here as the HTML form. So let's check it. So it's my simple predictor, estimated rent is, and so on. So just this thing, and put that as a result. So by that I have the form deploy. The cloud deploy, we have the function. It's simply here. We say HTML form. Yes, here HTML form, and then we say here string replace. So we say the estimated price is, and then we do here a marker. We say marker 1. And this is here. So we say for this form we want to replace marker 1 with our price. So this is the price we examined in our previous example here. And put that into the HTML code and present that not as text but as HTML. make that public again, and here we are. We got this global URL. We say Locarno, 100, 3 rooms, and the estimated price is 1,500 Swiss francs. And this is my simple predictor on Swiss real estate prices on a website. So I think I covered all the different aspects. It was long, I think more than 2 hours. But I think you need to get an idea of it. It's not important that you really do it, but you have to get an idea where the problems are. And the problems are parsing data, curating data. Key problem is getting data at all, because everybody is claiming it and trying to make business with it, and you don't get it. So you have to get disruptive via internet. If you have to go to Twitter and to OpenStreetMap and to have to get whatever you like, Instagram, or now these real estate portals, parse it there, but it's enough to make good things. So go there. So that's a key problem. Curate them, keeping in a proper shape, and get them in good proportions. Then it's very few things just to train your models or to complete your models, to make a prediction or whatever. And then again, and you get an idea of this, or we had it with these small maps. It's a problem as well to present it in a way that people like it. So it's another problem we don't want to cover here, but this is the principle how it works, and it needs other skills. You as an architect, I think you should understand these principles. So there's a data structure. It's always like a hamburger. The data structures, this is parsing, curating. Then you have in the middle, you have the tomato and the beef and or the veggie and the onion rings. So these are your AI applications, very few things to do. And then at the top, you get the interfaces in the web. And decoration interface needs special skills. And there's no way that you can, I think, in reasonable time learn that. What you can learn is setting up the idea of this kind of application, how it should work. What you can do is make experiments to show that it might work. And if you really want to do that, make your mock-up, like I did it here, make a nice presentation of it, and get Kickstarter money for it, that people can help on the curation, which can be done in India, and the interface design, which can be done in India as well. So, thank you for watching. The next extended example will be on images. Hope you see you there.